it's 300. Yeah, so it's about, it's around 300, so it should be around the same.
All right, so let's begin. I do have the summary written out for this one, so we have to write this one out, right? Right? So the first thing that we need to look at what do we do with forces? Right? What do we do with the forces? So we need to remember that the three main things that we do is that we kind of resolve the forces of it, right? Let's make sure I don't go you're able to look at the years and make sure we do all the years. Poly module 1 or 2. Too busy. Okay, let's check and make sure we do all the years. Right? So when dealing with forces, right, we need to remember that if we have a force at an angle, we need to be able to resolve, right? Adjacent is always cos. And the next one will be sine. So in this case, we just need to remember that the horizontal is not always true, right? It is sometimes, right? The horizontal component is f cos theta, and the vertical component is f sine theta. Right? There is a very popular example that we need to be able to put all the forces on. If I have an object here at an angle alpha to the horizontal, right? All the forces acting here will be weight, that's one. The component of weight here, which is W sine alpha, component of weight here, component of weight here, sorry, which is W cos alpha, and here is a normal reaction. Those are all the forces acting on that object at that point in time, right? So you need to be able to take any scenario and draw all the forces acting, right? And next popular one is the pendulum. What are all the forces acting here? All the forces acting here are what? Tension, of course, and weight. Right? And if you know here is theta, and we could resolve tension, we could resolve tension horizontally, and we could resolve tension vertically. Right? What is tension horizontally here, Killen? Opposite. So that'll be sine theta, right? Opposite is horizontal, adjacent to be vertical. Right? That's why I said at the beginning, it's not always the same. Right? You have to pay attention to where the angles are. Right? We should also note that we could write a force in a vector form. Right? So you have the x component by I. Sorry, let me use horizontal, right? Well, let me write x component, y component by j. The x component is this. And the y component is this. Okay? So we can write a force in a vector form as well, right? We could write it in terms of the two components, and we could write it in a vector form. Then if we have a system in equilibrium, let's say we have a system in equilibrium. F1, F2, F3. What are the two ways to solve for any unknown? Right? So the first thing we could do is we could say that the resultant in any mutually perpendicular direction is 0. So we can start by saying that the resultant force is 0. What's the next way to solve forces in equilibrium? Lambdas, right? Right, we could use Lambda's theorem. Right, two techniques for solving forces in equilibrium, right? Resolve mutually perpendicular equal to 0. Oh, wait, then write Lambda's theorem. Right, let's pretend here's alpha, here's beta, and here's gamma. Lambda's theorem says that F1 over sine alpha, F1 over sine of the angle from here is equal to F2 over sine of beta, F3 over sine of gamma. Right, Lambda's theorem, we use it. So again, if they tell you have to use Lambda, well, you have to. If not, you can just use the solver. Okay. Let's say this surface here is rough. What do we have to include here? Friction. Right? Friction acts, if it's moving this way, friction opposes motion. And friction is equal to mu by R. Coefficients of friction by contact. Okay, so add that back to your first diagram. And all right. That's Lambda's there, that is resultant force, and we include friction as well, right? So again, you remember when doing questions, what's the most important thing? That diagram, right? You get that diagram right, the rest should be easy. Right? After that, we have kinematics. Right, let me just make sure we remember all these things. Kinematics, right? Maybe I can block. Who pulls it up? Somebody will write this meter at a type over somebody's thing.
So that's what-
Yeah, right, on top. And this dynamic sum. We ever do a unit one cash loss? We did a unit one cash loss last year. Huh? Oh, that is somewhere.
Yes.
I did that type of somebody. For unit one?
Okay.
Yeah. You have one?
Yeah.
One. Fine. Country. Right, yeah, kinematics. Let's write everything for kinematics. Right, of course, you'll recognize that an applied question doesn't come differentiated. There's tying out everything. Everything is motion, right? So kinematics, we remember things like all the equations of motion, V is equal to U plus AT. V squared is U squared plus 2AS. S is equal to UT plus a half AT squared. S is equal to a half U plus V by T. Remember what all these three have in one. What do those three have in common? They all have acceleration, right? They all have acceleration. So whenever you're talking about vertical motion, you generally use these, right? So you use the for right? And you will see these a lot. You will see these in projectile motion. And I want you to remember to use them properly. So in projectile motion, you use all the equations on top for vertical motion, and you use velocity is distance on time. You use these for horizontal motion. Right? You don't have to learn all the proofs, right? But I'll still give you one or two I have here. I have one or two little proofs somewhere here. Right? You have a few proofs here. Right, like horizontal range. Horizontal range is U cos theta by T. Right, time for maximum height. U cos theta on G. Right, and you have the equation for projectile motion. R is the range, horizontal range. Like if it travels like this, here to here is R. What's that equation again? The one with the one for horizontal is minus tan theta x squared. Check any notes now. I'll have it. Maximum height. Specify maximum height. And if you put 2 here, if you put 2 in front, it's for the whole journey. It's the one that we proved. I think I have it in this book. Actually, it's something like it. I think it's y is equal to minus x squared tan alpha something like that. No, I think something missing. A G missing there.
Minus G power B square
Minus
G
over.
B square
So minus G over 2u squared
by 6 theta
by sec squared theta.
bracket 6. G by itself square A. So start in bracket.
Oh, the whole thing in bracket. All right. Okay. So
Unit X
x or x squared.
X square
X squared
plus start theta y
plus tan theta by x. So what it's saying is that at any point, you could find the vertical displacement by plugging in x and y, right? Let me just run over that there first. If you shoot a particle with u at an angle alpha, the projectile is normally like that, right? At any point in time, y is this displacement here, x is this displacement here. So if you want to find y at any point along a projectile like this, you can use that formula. U is the initial velocity, g is gravity, x is the horizontal displacement, right? But you don't have to. You can get that from this, right? You can get it. See, everything here, you're getting it from me. But they learn this and learn six together. But if you have plenty memory space, wait, right? If you have limited memory space, focus on it, right? We have plenty all over. Plenty. So you have that, you have kinematics.
design in bracket.
Maximum height. Time at maximum height. Right, so that's the first part of it. Next thing we need to remember. The number is time graph, right? Right, remember Newton's first, second, and third law. They don't ask the laws, but the first law has to do with constant velocity. What does constant velocity imply? Constant velocity implies no acceleration, which implies no resultant force. That's the first law. Second law, resultant force is equal to mass by acceleration. Right? From that second law, we can also talk about momentum. Momentum is mass by velocity, and impulse is the change in momentum. You'll see that? Impulse is the change in momentum. Okay, so resultant force is also impulse over time. Third law, right? Third law is like connecting particles, right? F of A is equal to F of B. Those are the connecting particle questions. Yeah, minus. Right, let us say it moving this way. If it moving down like that, then we could say that WA minus TA is M by A. Same thing here. TB minus WB is M by A as well. The masses are the particles, right? So I'm squeezing a little A there and squeezing a little B down there. Right? Right, copy that down. Okay, so those are all the forces that we need, right? Right, oh, you have a little space here, man. Have a little space right here. Last thing we need to remember is work. Work done is force by distance moving that in the direction of the force. And the power is work done on time or force multiplied by velocity. Right? We also have to remember that the conservation of energy, right? So the change in potential, for example, will be the gain in kinetic. Right? We need to remember the conservation of energy. Right? You should know what is potential energy, mgh, and kinetic energy, a half mv squared. Right? So those are the things that we need. Those are the things that we need to know for mechanics. Right? Mechanics is not just about knowing it, but it's applied. That's why it's called applied. Right? So let's see if we can apply this, right? Let's start off with some easy ones and then we'll move to some harder ones, right? Any questions on anything? Right? Any question again, please try to get a diagram. Right, let's start, right? Yes, iPad charger. Yeah. Oh, iPad charger. Let me mention it. No, my iPad charger. Oh, sorry, okay. What's the name again? Huh? Why the question is doing my turn? All right, let's start. Hold on, wait, no, one minute. All right, let's start 2022. Let's start with 2020. Everybody have it, right? So we're trying to do 4 and 5, right? Sorry, 5 and 6, right? And then to number 5, and when you finish at 5, you correct on 5. 2022, number 5 and number 6. How's that? What do you do? Yeah, start with 5. Right, put your diagram together and it's easy. Right, it's not much about it, so do your diagram and call me. I want to take a look at it. Well, we all copy it, so let's look at Judo, right? Try and put it together and then we work it out. So easy to start together. Right, so I'll take a look at it. I'll look at yours. Next up. Trying to get it on the group rest, get it. It's on the group writing paper. Yes, ma'am. Somebody can just send 22, 23, 19, 21 to Caleb, please. Type all except 19 on the group. Yeah, no. Drawing diagram, when you think you have it, call them, or you can come. Or you can say nothing, and that's what game I showed. No, I guess I didn't call your name. Finish. Right, what was it? Finish. Come now. Right, that you go. I was like, I'm trying to so they give you the block, right, boom. It rock, right? Boom. You're missing a force.
Yeah.
Right, but you're missing a force. It's pulled upwards along your rock. Here you're missing some forces. Well, you're missing the reaction, you're missing the components of this. Alright, now we will need to solve it, right? So you have this, you have the force, we're gonna see it, right? The equity force. Like it on the ground. Yeah, but every block is pulled upwards. Why a friction going upwards? Every block being pulled upwards. So what are the friction market? Right. And you missing direction. Yeah. Yeah, missing that. Then for the components, I try to find what you need. And we diagram again. Ready to see it now? Oh boy, you know, you bring two book now. Stop walking on top of my chair now, boy. What's it on next time? What's it on next time? Force. Very nice, right? That's force. With power. Right. Right? Very force. Whatever can be more with fear. You are right. Enough with our rules. Direction important, you can be up. Yeah, But this man going this way, right? My mom is going that way, mom. It'd be close enough. Right, these forces are components, right? So those, what kind of forces are? These should be broken like. What's this? So you think soon also? No, this should be down this way. Perpendicular to this, right? Broken line. And why a friction after this way? Yes, right, perfectly right there. And it's going to 95, yeah, it's 195. 95, but you were already. What friction? What friction? Friction. Right, friction after the outside. As velocity is here for the left side for the second of correct. These are broken. These are not, you see, they want all the forces after, right? So these are broken, right? Because these are components. Okay. The next part, we don't need to and now we put it. Yeah, right now. Yeah, the final. You don't know friction?
That's not 95?
Huh? No. 95 is a force being applied.
Oh.
And friction in the direction. Friction no always act that way, you know, in that diagram is sliding down. You come back here again. Wait here, what you can push here. Right. Right, take a break. Okay. have friction here. And it's moving upwards. And when I go in 95 meters. And this will be a component of this. So what my diagram? Down here, W sine alpha. Okay. W is done. W is done. And this will be component. This will be W sine. Oh wait, gravity is what? Oh, okay, good. You gotta pay attention, right? Sometimes the use gravity to tell. Right? Let's see if we get a diagram, right? Well, I saw a diagram. Let's see. Where's the dot stuff? Right, let's check out the diagram. Right, you'll have a question, right? So let's take it a talk here. We're doing that 22 first. Diagram, most important thing, right? And I'll start with some easy ones first. No, that is it. So what we kind of forget is direction. Right, so for this one here, diagram, most important thing, you have your horizontal, you have your plank. Here is 30 degrees on your plank. You have the weight is 80 newtons. You have a reaction force and going this way. So therefore you must have friction, which is mu r. And then they said it's on a rough plane inclined at 30 by a force of 95. So there's a force of 95 newtons pulling it upwards, right? That's what a complete diagram looks like. That's what they want in party. And then you could put in the components of this. The good thing is here is always 80 cos, and here will be always be sine. Right? You don't need the dotted part for the first part of the question, but you need it for your next part. That's okay? Right. So your diagram will look like that. That's the most important thing. Next, acceleration. How do we find acceleration? Acceleration is what? Look through all the formulas motion I think you would use. Right. Acceleration is resultant force. And what is here? Highlight resultant force, right? Over mass. Do we know the mass? Do we know the mass? Yeah. Resultant force, right? Watch up here, Ollie. I want you to remember Newton's second law. Newton's second law says that the resultant force and the acceleration in the same direction. What direction will the acceleration be in? Along the plane end. So you have to find the resultant force in the same direction. Okay? Along the plane. So you have all your forces there, find the resultant force. Take your time. Find all the resultant force. Is there any vertical motion? Is there any motion here? Motion. No, all the motion is here. So what you can say about these two forces? The equivalent or the equal. Right? The particle not moving like that. It's moving along this plane, parallel. Right? So therefore you only have motion and you only have a resultant force here. Here will be 0. That's okay? Go ahead. Try and see if we can find the acceleration. Yes. Yeah. Go on, go on. Between 5 and 6, with 6 hours jumping. I love her, get us some, get up some. All right, let's check out the acceleration now. Right, so what is the resultant force? The resultant force is going this way, right? So that'll be 95 minus 80 sine 30 minus mu r. Mu is what, 0.4? Mu was 0.4, and r is equal because these two forces equal, because there's no motion vertically. R is equal to 80 cos 30 all over 8. Right? In a Casio, write the exact value, right? The solution will always have exact values. Okay, what happened there? So you see how we apply Newton's, second law, we apply equilibrium, we apply a few things and resolve it. How much is this? Oh, yeah. 3.41. Yeah, that's all right. 3 significant figures. Yeah, Saskia? Papa. Take it back and see, make sure I calculate it. Right? Make sure I did degrees, right? You didn't get up? You follow what it? No? Highest time is resultant force. I give you a object. Highest time resultant force. Minus 7. So highest time resultant force here. So it'll be this minus this. Nah, you had to find R, because you know I'm US, so you had to find R. And the only way to find R. Huh? Sorry. R is 80 plus theta. The power there. Subtracted by 95, but you still get only 20, cos 80 cos 50. Yeah, you gotta subtract out 95 as well. Right? Fix it up, okay, diagram for your next one, everyone ready? Next one is what? What, it all nothing else to this, okay.
Yeah.
Open it up. Right, so we done the acceleration part, that is 2 and 6, 8 marks, right? Next. Next, they gave you a diagram and told you to use Lambis. So that means they get all the angles, right? What's the angle between T and 15, Kaylin? 90 plus theta. What's the angle between T and 40? Grant? Alright, 180 subtract theta. Alright, and between 15 and 40 is what? 90, right? Yeah. Go ahead, apply Lambis and then solve for theta. Remember you need what? Sine A plus B, right? Right, they want an equation using Lambis, they want an equation T into theta and then find theta. So which one's the best two to use? The best pit to use it, which one? Put it on the left, right? Okay.
So you can put- I said you want, and I'll help you, that's.
So we end up with, again, we're not using this one, this might be a little bit harder. We're using these two to develop the relationship, right? And that's what they want? Right, so that would be T over 1 is equal to 40 over, expand this one time. So that'll be sine 90 cos theta plus sine theta cos 90. Right, this will be T over 1 is equal to 40 over sine 90 is 1. Cos 90 is 0. Cross multiply, and you'll get T cos theta is 40. All that for that? All that just to get that? So we have two unknowns there. So we are the next equation. That's okay. So that is the first equation. Then they want you to find theta. But we can't find theta here because we don't have enough info. Are you okay with that? Are you okay with that? So we have two unknowns, so we have to go back again and get the next one. So we have to use here and here probably. Or could we use here and here? Anybody use these two and get theta? These two? And get theta. You use these two? Oh, yeah. You can use resolving to, they didn't specify after that. Yeah, that's true, Jude, right? That's true. They didn't specify to use Lambda to solve it. So because it's system in equilibrium, we could resolve now, taking this off. Right? We could resolve T, where was theta? We could resolve T, here will be T cos theta. Here will be T sine theta. Right? These two will be equal. T cos theta is 40. T sine theta is 15. Right? T sine theta is 15. T cos theta is 40. Divide, and you'll end up with tan theta is equal to 5 into this is 3 on 8. Theta is equal to tan inverse 3. How much is that? Huh? 20.6. What do you use? Here, use this as well. What you do? Expand this out. Okay. They didn't specify after that. We already did what they wanted. Right? So you didn't have to go on, but I could. I like that. Right, one thing next one time, everything you know, everything in 22, everything in 23. Those things. What they ask for after? They ask the value of tension. So just plug it in anywhere here now. Plug it in anywhere. T is equal to 40 over cos 20.6. How much is that? 42.7. Right? Let's go again. Take a look at part C. Right, again, if a diagram possible, write it in. I mean, draw it in if you need a diagram, part C. Take your time, no rush, we are real time. Right, draw a diagram, see if we can figure out part C. Right, but the part C, draw the diagram, and then let's look it out. So it hits the wall, and when it hit the wall, it bounces off, right? You want to define impulse, so that's basic, right? Impulse is what? Impulses, change in momentum, mv minus mu. So that will be 1800 by 14 minus 20. Right? So that minus what? 61,200. SI unit is kg ms minus. Huh? How you know? It don't matter. It don't matter. Change in velocity is what you're interested in. Right? Minus because it's a force that slow it down. Then get 61,000. Should we multiply that, right? Same value to use, right? Oh Lord. Oh, that's what I was saying. Okay, that's not. Right, but remember, impulse is the change in velocity that occurred. And the change in velocity is during the collision. So the impulse, and next way to put it, impulse is force acting per unit time. Right? So the force acts when it hits the wall. Okay? So during that period there, the change in velocity was 6. So this is what you're using. Change in velocity. Right? Do I put the sign? So it'll be what? 10,800. The next one. So don't worry too much about it. Yes, the sign change. Huh? No, it's negative because it's a force that slow it down. Because it's charged force. Try the last one. So a particle moves in a straight line, then get a equation here. A particle moves in a straight line with an acceleration, right? So you have to, of course, write all the important things. The question said the acceleration is proportional to t squared, where t is the time in seconds. When t is equal to 3, the velocity is equal to 5. And when t is equal to 6, the particle velocity is equal to 10. Derive an expression for velocity of the particle. Right? I did not. Right? I did not give you this. I forgot to give you this. But remember, you have displacement, velocity, acceleration. When you go down, you differentiate. When you differentiate velocity, you'll get time. Right? But if you have acceleration and you integrate acceleration, you get velocity. Integrate velocity, you get displacement, right? I didn't give it that, sorry. So here, acceleration is equal to kt squared. But we have a problem. Right? Acceleration is dv dt. Okay? So how are you going to get v? What you have to do? Huh? Yeah. What you have to do? You have to integrate. Right? You have to integrate. So integrate velocity. Go ahead, have fun. And use the information to get it. Right, that's correct, out 22 and 23 now, right? Right, what we got here? When you differentiate, well, sorry, when you integrate. Right, when you integrate, you'll get V. The integral of this will be K T cube on 3 plus C. Problem, we had to get rid of K and C. Right, so when T is 3, K is equal to 5. So 5 is equal to K. 5 is equal to K by 3 cube, sorry, plus C. So that'll cancel, so you'll get 5 plus 5 is equal to plus 9K plus C. Right, that is your equation 1. And then when T is equal to 6, V is 10. So 10 is equal to P by 6 squared over 3 plus C. So I am getting 10 is equal to 36 divided by 3 is 12 plus C. Anybody get that? P and C? Huh? Oh, sorry, it's cube. Sorry, cube. How much is that? Why 6 cube on 3? Huh? 72. 72 key. Subtract, and you will get minus 5 is equal to 63. So I got K to be 5163, and then it go and find C. Once you have K and C, come back here and you finish. How far reach?
I just believe this right there.
For reach here? So what do you think the information was for?
Right?
Right? So there are these questions where you have to model and you're using that. Next part. What's the next one, Olga? That's number 5. That's the first one that killing. Well, define C. You define C is K and C are defined. Fix it one time. C is what? Huh? 13 and 7. So you end up with V is equal to what's 5163 divided by 3? Well, when it's subject to K, 5136 divided by 3. Yeah. Right, so this is your equation that they asked for in part D. Next one. Connected light string, acceleration, tension, basic. Number 6, kill off that fast. Number 6A, move out that fast. Fast. Posing one more, very answer. Oh, yeah. Look this way. Busy. Bye-bye. Well, you have to know. Start part 6, but don't take it long already. Oh, yeah, we do a part 6. Or taking long. I tell all to finish all the thing, so when I come, just need to correct. But I want to sit down with modern warfare and thing. You can play people. Good. Yeah, they have to play a lot. Oh, yeah. Let's run to 6, please. Just go to the whole of 6, please. Don't stop to watch nothing or play nothing. Oh, yeah, do 6. Don't get it too slow. Finish up. Let's go to 6. Oh, wait, what time is that? Finish. All right, oh, yeah, they're gonna need to do this one. Right? And tomorrow, yeah, say, homework, you can try 33, 21, 19. Right, one, all. Homework. That's a joke tomorrow. Some homework. Tomorrow, we'll finish up on that. I'll send. I have it. Right, so it won't take too long. I'm gonna start up this. First one easy, right? It hard? Right, first one. right? So it will most likely move in this direction, right? And then we have to include a little part here about the distance, right? So we set it up real fast, and we know that, of course, we are applying F is equal to ME, right? We know that 120 minus T is equal to mass by acceleration. And we also know that T minus AT is equal to AT. And I'm going to add. This is 40 is equal to 20E. A is 2. Everybody get up for A? And then T is what? T is 96 newtons. Yeah? Yeah, one more figure up. 96 is it, right? Yeah. Another watching? Oh, you watching Game of Thrones? Sorry. Determine the distance traveled by each particle after 6 seconds. So you want that's part 3, right? Part 1 and part 2. Always part 3. Well, get it right what you have, right? So distance traveled by each particle, they will travel the same distance, right? So they want in 6 seconds, we know the acceleration is. We know the acceleration is 2 and the initial velocity is 0. So what do you think you're going to use there? Distance formula, very wrong. You have acceleration. Equation of motion. S is equal to, right, S is equal to UT. What do you now say? Well, you didn't see that formula? Man said distance formula. You didn't see equation of motion. So that's 0. This is a half by 2 by 6 squared. All right, so that's 36 meters. They both travel 36 meters. Have more? What's the part 4? I mean, the half velocity. The initial was 0. Remember, I start from rest. So now the particles like this. So now the particles like that. I think they want something with the 12 kilogram here. So the 12 kilogram is somewhere here. Right? And that distance will be 100 minus 36. I think looking good, but yeah. You find looking good? All right, looking real good. That purple starts off nice, but then the purple started to give some trouble. But so it dropped a little bit lower, right? So what do you want? Of course, it's moving, so you might need a velocity here. So they want the velocity of the 12 kilogram particle just before it hits its ground, if it is disconnected from the string 6 seconds after the system, right? So it has no more string on it. They want the velocity just before it hits the ground. So we know the distance to cover is this. What else we know? Would it have that same acceleration? Would it have that same acceleration as before? Huh? No, it disconnected. So that acceleration was a connected acceleration. So they're not there anymore. It's free to move. but we need something. We want to find V and we have S. So you want to find V, we have S, right? It's not connected, so what will the acceleration be? Gravity, very good. Modern warfare, you're getting on modern warfare. That's 64. V is V. Right, but we need something else to use the equation. What we need? Well, which equation have Vs and A in it? Second one. Right, second one is V squared is U squared plus. Sorry. So we want to find V, we need U. We need U to find V. Like that, bring U there. Where you get lost? Where you get lost? Tell me where you get lost. From part 4? Not far, you're right here. So imagine this. You have a particle. Forget everything now. It's disconnected. This particle will fall, right? And it will fall with an acceleration of G. Correct? It's fallen already because it wasn't released, it was already fallen. So it will have an initial velocity, right? You want the velocity just before it hits. And the distance covered is 64. And question say after 6 seconds, it traveled 36 meters. So the distance remains is 64, right? So diagram is important. That's all the information given there. But we want to find V, but we don't know U. We have A and S, so we go to we don't know U. U is not 0. U is not 0 because it didn't start from rest. It was moving already. It was moving, but now the string going. How we getting U earlier? How we getting U? You tell me, how we getting U? How we getting U? Huh? Satisfy with that. The next equation. Of course, I have to use the next equation.
And then I understand. Also, yeah.
Use which first equation? So if I use you want me to use V is equal to U plus ET, right? Substitute here.
Yeah.
But I don't know V. I think I try and then. But I think it's correct. This is the equation you have to use. But try to remember this. All right. No, you think. Think about it. I'm telling you. The only hint is you have to use that equation. No, right. Think. Huh? Yes, you have to substitute. What you're going to substitute? And you want the initial velocity here, and you want the initial velocity here. No, but you still don't know V or something. Nah, it can't do that. So you want to put V back in here. Yeah, but you don't know U. You don't know U. All right, let me give you our next thing. This initial, forget this new system. Forget part 4. Forget part 4. Forget part 4, right? Can you find the final velocity in part 3? Yeah? And you can find the final velocity in part 3. Final velocity in part 3, the initial is 0. We know the acceleration. We know the time. Won't that final velocity be the new initial velocity? And what do you think? So the particle falling, and when the string bursts right here or removed here, it falling, right? And it will continue to fall with that last velocity. That's clear. The final velocity when the string was on, the final velocity when the string was on is now the initial velocity when the string is off. No? Kind of making sense? So what I'm saying here is that I can find the final velocity when the initial was 0, the acceleration was 2, and the time was 6. So that was 12 meters per second. And now this final velocity is equal to the initial velocity in the next phase, that's part 4. So that initial velocity is 12 squared. It's going down, gravity is 10, and the displacement is 60. And that will give you the velocity, and then you have to square it. What's the velocity? Final. Hmm? 10. Question 10, I think. Gravity 10. Right? What was the last part? So that part 3. Oh, what was part 2 then? No, that's about in B. Push up, I really did the wrong thing. So what the velocity? How much? 37.7. So the value is 37.7. Okay, I really wrong. All right, we'll take right along. Anyway, so we'll continue from right there tomorrow. Right? Take a little break for building because today is module 1. Right? So I want you to finish up the rest of the homework in 2022 at least. At least throughout 2022 homework. All right, take a little break. Take a little